Hello, my name is Alexandre Bergel, and I will present a paper called Generating Object-Oriented Source Code Using Genetic Programming. So this is a joint work with Vicente and myself, and we are from the University of Chile. So source code generation is considered as a difficult, challenging, and very promising research area. So source code generation is essential for other research areas such as bug fixing and software auto repair. And furthermore, source code generation is really the primary target of genetic programming. And in this paper, our paper is about using genetic programming to generate source code. So we'll focus a bit on genetic programming now. So genetic programming maintains a population of individuals, and each individual is a program. And this program is expressed using a tree, which is called the abstract syntax tree. At each generation, the genetic programming evolve individuals in order to create better, more fit individuals. And then the algorithm uses some genetic operators, such as the mutation and the crossover. So at each generation, genetic programming improves the quality of the population, and this evolution is driven by a function called the fitness function. The fitness function evaluates each individual by compiling and executing the program. And so here's a small example. If I have this expression here, and this expression can be represented using this tree here. Okay, and if I have two individuals, one on the left and one on the right, and these two, assuming that these two individuals belongs to the same population at a given time, then the new individuals can be formed by recombining part of those trees. For example, here, this node here can replace the previous one in order to form a new short program. And hopefully this new program will be better than two parents in terms of the fitness function. Okay, so source code generation has been the topic of XC paper in 2009. This paper is titled Automatically Finding Patches Using Genetic Programming. So this is a program that uses genetic programming to generate source code to fix bugs. So in this paper, genetic programming is used to generate source code, and all the experiments were conducted using the C programming language. So C is a statically typed procedural language, which means that for a given piece of code in C, the statically type means that each variable has a type that is known at compile time. So we know exactly at compile time, statically, we know what is the type of these variables. It means that during the execution, we know the range of value that can be accepted by those variables. And furthermore, each function knows what are the inputs typed and what is the output. So we know that, for example, the check prime number return an int, for example. And furthermore, C is a procedural language, which means that whenever I refer to a function, I know exactly statically which function will be executed. The same piece of code written in a dynamically typed object-oriented programming language, things are very different. Even though on the surface that looks a bit similar, but there are some profound differences. For example, all the variables, there is no type information. It means that we do not know, for example, that n must refer to an int or color, a string, whatever. So it's just a variable that we have no idea of what during when this function here is called, which kind of value we should provide. And furthermore, when there is a reference to a function, to a method, then we don't know statically which method will be executed. We may have several implementation of the square root function in the systems, but statically we don't know which one we will use. So it means that generating source code for a dynamically typed object-oriented programming language, then there is is much less deterministic than using a statically typed procedural language. So dynamically typed object-oriented programming languages are very, very common those days. So here, this is the list of the most popular programming languages and currently used, and those are the ones that are dynamically typed, and those are also the ones that are object-oriented. So, and currently we do not know whether we can apply genetic programming to generate source code for those languages. We know that it works for the C programming languages, but we do not know whether we can use genetic programming to generate code for those languages. So this is exactly what the scope of this paper. So the research question we have addressed is whether genetic programming based source code generation can be applied to dynamically typed programming language. And our short paper explored the use of genetic programming to generate object-oriented source code in a dynamically typed setting. The results show that for one-line statements can be generated with a precision of 51%. So it means that just to produce one line, one single line, genetic programming can be used to generate those lines, and we have a precision of 51%. Okay, so for our experiment, we use the Faro programming language, the Faro Smalltalk. So Faro is a very simple and highly expressive language. All the computation is expressed using objects, and objects send messages. And this reduces significantly the amount of for the search space. I mean, the number of different kind of nodes that must be involved into IST. This is extremely reduced to essentially two syntactic constructs: message sent and variable accesses. Since in Faro everything is an object, and object communicate each other by sending messages, we just need to care about message sent and variable accesses. There is no operator, for example, to express arithmetic operation. There is no operators to create instances of variables. Everything happens by just sending messages. And furthermore, like we focus on generating one line of code, and so we use genetic programming to generate the body of an arbitrary design method. So we have one application, and in that application we pick one method that has one statement in it. So the method is long of one statement, and then we are looking at how genetic programming can generate the body of that method. So we're focusing on method that have exactly one statement, that body, and the reason is to solely focus on the code generation. We are avoiding all the location of the generation as was done in this 2009 XE paper. So here is a short example. If we have the method called max value x that is defined in the class as abstract plot, and this method has just one statement as in definition. It returns the value written by the expression self-defined values x max. So in Java, this expression here will be written this dot defined values x dot max. So whenever there is a dot in Java, in Faro, this is a space, simply. And the question is whether genetic programming can generate this expression here. So the methodology is the following. Just to give a brief overview of what of methodology is the following. If we take one application, and each pixel of that picture here, each pixel is one character of that application. So in the middle of it, we have our expression self-defined values x max in the middle of it. And if that application comes with some tests, let's assume that there is 10 unit tests and the 10 tests are passing. If we remove that expression, if we put a hole in it, like we remove that expression, we have, most of the tests will fail. Maybe not all of them, can say that there is one test that passes, but all of them are failing. The genetic programming algorithm, we try to fill this hole with an expression that try to maximize the number of passing tests. The genetic programming can try to fill this hole with an expression, maybe this one. This one, self-defined values x, is a bit better than just having an empty hole because some more tests are passing. And then the algorithm, like through the evolution, is trying to maximize the number of passing tests. It can come with that expression until the evolution leads to the correct expression that we have removed. So the genetic programming is searching for the expression that maximizes the number of passing unit tests. That is really the essence of our methodology. So the overall like a workflow of our work is the following. So we have 7 steps. The first one is to pick an application that has some tests. You know, we have the application, we have the test, we run all the tests, and while we run the test, we monitor all the values that are passed as an argument, all the values that are returned by methods. And then also we extract the call graph, you know, like which method are calling which other method. So once we have run this test, the unit test, and we have all the information about some information about the execution, then we can infer what are the classes that are involved in the application. So is, you know, understanding like which libraries this or application is calling is the first step. Like what are the classes that might be involved into the overall executions. Then we can deduce the method signatures from all the values that are passed around. So we have a signature that we infer, and then we also can use all this information to identify what are the syntactical elements that are likely to be called during that must be called during the evolution. In particular, like, you know, which methods are likely to be called, which variables are likely to be called to be accessed. And we use the methods that are covered by the test executions, and also we may use some variables such as this, the self this. So we have a number of hyperparameters, and in particular, like when we call a method or when we involve a class during the evolution, then some classes are more likely to be called, some methods are more likely to be called than some other one. So those are some hyperparameters that we identify using some static analysis on a large corpus. So from a large amount of code or faro code, then we compute a number of metrics that are used to weight the probability to pick a particular element. And then we generate the code using genetic programming. We compile all the generated methods. So we have the application, we have a hole. We try to fill the hole with each individual of our population. We run the test, and then we can identify the best individual. So we have two weight mechanisms. So the priority can be used. You know, priority of some elements can be employed whenever we want to do a mutation or generation of a node. Now we have two weight mechanisms. The first one is uniform, saying that all the methods and all the variables have the same priority to be chosen. And we have the similarity weight, which means that if we try to fill the body of a method, we look for other methods in the system, and we try to use the weight determined on the other method that have the same name. So the intuition behind is that if I have two methods that have the same name, then, you know, it is likely that the body will be similar. And that's really the idea behind this weight mechanism. So as an experiment, we took the Russell application. So we took a part of Russell. In Russell, we picked 99 methods that have exactly one statement. So these 99 methods have mutators, setters, and some other method that we qualify as complex. A complex method for us is a method that is not a mutator or a setter. Then we have 68 unit tests, and then we run the experiment, and then we compare the different weights as uniform or similarity. As a result, we have the following. So our approach works particularly well for the accessors. Okay, so either uniform or similarity gives over 90% of precision. For the setters, also we have relatively good results, particularly for the similarity. But the most interesting aspect here is the complex. You know, complex, it means that the genetic algorithm, the genetic programming algorithm is trying to generate the body of some functions that are not trivial, and we have a precision of 12%. Okay, so that is our presentation. So we presented an automated technique to generate dynamically typed object-oriented code. And our approach is to use genetic programming algorithm and a weight mechanism, weight systems. We try different weights without having a significant positive effect. Overall, we have a precision of 51% and 12% for non-accessors methods, so that we qualify as complex method. Okay, so that is the presentation. So our approach is about generating methods that have exactly one statement. We pick one application. We have a hole, and the genetic algorithm is trying to fill this hole by using the number of passing tests. And we have a workflow that describes different 7 steps of methodology, and then the results is giving us like 12% of precision. Overall, 51%. And overall, but then it's 12% for the complex method. Okay, so thank you very much.
Hello, are we live now? Could someone confirm in the chat? Maybe a few more seconds. Yes, we can. Okay, good. Thanks. So we have first question from Wes. Some other APR approaches, like those that operate on defx4j, do handle object-oriented programs, but typically aren't doing this sort of object/method inference you describe. How do existing approaches compare to your performance for accessors, setters, and etc.?
Yeah, I mean, that is a very good question. I will disappoint Westlake with my answer. So basically, I think we do not really know. Like, the starting point was the XT 2009 papers. And yeah, so that was really the starting point, and we were trying to replicate some of the results this paper had, but we were left in on the way to do that. So, but yeah, so definitely we will have a look at that. So yeah.
Okay. So I have another question, because I haven't heard of Faro programming language that you use. So could you comment on how does it differ from? I mean, you mentioned it's kind of like Python, but is there something more specific? Like, did you have to modify the mutations somehow to adjust to it? It looks different. So I'm into it.
So there is a number of I like Faro very much. So one of the things is Faro is extremely simple language, like much simpler than Python. Python is actually quite a complex programming language, but Faro is extremely simple. Everything happens like with objects, and objects communicate, each other by sending messages. So sending a message is really the key aspect of the thing. And all the IST is extremely simple. Methods are extremely short in terms of, like, the IST of methods is extremely short because of this homogeneous way of carrying out computation by sending messages. And so that's for the programming language aspect. And the programming environment, which is absolutely fantastic, the one of Faro, this is live programming environment, but it was not really that beneficial in that setting. Even though, like, maybe we didn't have to pass pipe because everything is memory, and yeah. So Faro is a cool programming language, I think.
So which domain is it like mostly used in?
It is used as, there is a relatively large community behind. Personally, we use Faro a lot to do some visualization of software visualizations, and and software re-engineering, software reverse engineering, software analysis. So this is where, at least me and my group, this is where we are using Faro the most.
Okay, I have another follow-up, but I'll first read prioritized questions from the chat. Another from us. For the more complex situations where you are getting much lower precision, what do you see as the big challenges? For instance, is it the search space for composed method invocations, the fitness function? What is causing the lower precision?
Yes, so trying to not really a good baseline. So for example, like we have an algorithm, but we don't know like how comparable is it with human, because maybe the task is simply too difficult. Could be. Maybe there is some things, there is a notion of context that is not apparent in the way that we feed the algorithm, genetic algorithm. So why we have low precision at some point, we don't know. But something I suspect that a human will not be significantly better. That's, I think, our guess. So we don't know yet. But maybe the search space maybe like is too complex, and we feel that there is a notion of context that somehow is missing. Like if I just provide a piece of code, well, I mean, it's very hard to understand like what it does. You need to understand to give more like everything that is around this piece of code to really be able to interpret what some crucial aspect of it, I think. I don't know whether, Vicente, if you want to compliment, then feel free.
Okay, maybe I'll first actually ask Bobby's question because it's related. Perhaps instead of making GI work with a programming language, we should think about what features a language should have to make it a good target for GI. Do you have any thoughts on this, given your work on trying to get GI to work with object-oriented and different typing systems?
Yes, so that is a very, very good question, and like the naive approach we have taken is to reason on the IST, but there is something more. Like a human will not be able to be much better than our algorithm. So it means that something is basically missing. But humans are able to program, but you will not just look at the method. You will look for dependencies. Like just the name of the classes. It tells a lot. The name of the method, the name of the variable. Who is calling the method that you want to actually repair, and so all this notion of context is currently I think is missing, and this is where I think we should at some point develop. So we were kind of trying to do that with the weight mechanism. Like if a method, if two methods have the same names, then maybe part of the body can be kind of similar. This is something we just experimented with, but I mean some more work is needed to be able to express, to formalize notion of context that I think are absolutely central to in order to be able to feel whole in a program. So.
Okay, thank you. And one more question from Bill. Do short modules make it easier to use GI on, in your opinion?
Yes. By module, I think that we are talking about methods. But yes, like the fact that the method in Faro are very short, like just few lines of code. Most of the methods that define a typical Faro program are very short, like much shorter than if it would be in Java, in Python, or in C. And yes, so it makes it indefinitely better to use genetic programming, at least because like there is less uncertainty. I mean, there is less possibilities for the location. If you have a short method, then like what do you want to repair? It is easier to identify what has to be repaired instead of defining a portion. But again, here we are focusing on just one single method.
Sorry, I have 2 seconds left, so we might cut out.
Hello,